Alright, so I am going to look through the 2008 Physics GRE test. To my knowledge, this was the actual GRE given out in the year 2008. So I'm going to go through it. There's 100 problems. I'm going to go through all of them, and in this video I'm going to go through questions 1 through 10. Something to mention, though, before I start is I'm going to try to tailor this as if somebody was studying for the test. So I'm going to assume you've seen at least some of this stuff before. Obviously, I'll remind you, but I kind of want us to be able to get an answer quickly, how to be able to eliminate answers, because it's in the context of wanting to do well in the test. So I'm trying to keep that in mind as we do it, because it is a very fast-paced test. So let's go ahead and get started with question 1. It says and also, if you wouldn't mind, please like and subscribe to this video. It helps me out a lot. Hopefully I can help you out with this. So question 1 says, a ball is thrown out of a passenger window of a car moving to the right. Ignore air resistance. If the ball is thrown out perpendicular to the velocity of the car, which way best depicts the path the ball takes as viewed from above? So right off the bat, I think we can pretty easily get rid of E and D as options. That's pretty silly that if you throw the ball out, it's going to... Maybe if you didn't ignore air resistance, that might be a more accurate notion. But we're ignoring air resistance, so you can assume there's no forces acting on it horizontally. Or, yeah, I guess you would say in the X direction. So because there's no forces acting on it, it's going to continue along this straight line. Answer choice B. And it makes sense because there's no force acting on it whatsoever. There's no reason for us to have any acceleration or change in velocity. It should continue along that straight line there. There shouldn't be any of these curves. That would imply some sort of something happening to alter its movement, which isn't happening. Again, if we're ignoring air resistance, that's pretty key here. If we weren't, then it would obviously look different. I don't want to be too in-depth here. Hopefully that makes sense. Number 2. So number 2 says an object is thrown from an open window of a building. Its initial speed of the object is 20 meters per second. And it hits the ground 2 seconds later. From what height was it thrown? Neglecting air resistance and assume the ground is level. So for this, we're going to have to use some kinematic equations. So this one will be for 2. I'm going to go ahead and write down what we know with y. Let me do this over here. So this is for 2. This is how I like to do my kinematic equations. I like to write down everything we know and go ahead and insert values. And the reason why I did y is because ultimately we're looking for the height it was thrown. So basically the height of the building. In other words, we're looking for our initial y. We know that it hits the ground, and the ground is level. Let me make that a little smaller. Hits the ground and is level. So that means our final will be 0. If it's just given a velocity in the y direction or in the x direction, there will be no y initial velocity. The man's just throwing the ball straight out of the window, giving it only horizontal. So it mentions here that it is thrown horizontally. That's important. Acceleration, we know that's going to be g, and we know that this is 2. So we can use our kinematic equation here. This is going to be the most famous one. You're going to want to memorize this for the test. Y equals y initial plus v naught yt minus 1/2 gt squared. I'm actually making a LaTeX doc with all the equations that I need to remember. So maybe that's something I can share. Okay, so we know this would be 0. We know this would be 0. So then y initial, the height of the building, is 1/2 gt squared. 1/2 9.81 times 2 squared is 4. So 2 times 9.81, that's going to be about, I don't have a calculator with me, but that's going to be about 19.6. So a little kinematic equation there. You're going to want to remember that equation, but that's all there is to this. Okay, so number 3. So for number 3, it says we have a resistor in a circuit, and the energy, it disperses energy at a rate of 1 watt. If the voltage across the resistor is doubled, what will be the new rate of energy dissipation? So for this, we're going to use P, that's our unit for watts, is equal to VI. But we know from Ohm's law that I is equal to V over R, because IR is equal to V. So then we can take this equation and plug it in here, and we get P is equal to V squared over R. So if you double the voltage, it's actually going to go up by 4, because we have to square it. So if we say V equals 2V, then P equals 2V squared over R, which is 4V squared over R. So it increases by a factor of 4. Okay. Again, those are some equations we need to know. So that was 1, 2, 3. 4 is this one. Okay, so for 4, it says an infinitely long straight wire carrying current, I1, passes through the center of a loop. Of wire carrying current I2 as shown above. The long wire is perpendicular to the plane of the loop. Which of the following describes the magnetic force on the loop? So they want the force on the loop itself. Like, say here. Anywhere on the loop, I suppose. Well, it's not going to have any sort of, it's not going to feel its own magnetic force. The only force it would feel is from I1. So I1, if we use the right-hand rule, if we put our right thumb in the direction of that, we're going to have current that, for example, here goes into the page. So if you put your thumb in the direction of I1 and curl your fingers, that's going to go into the page. And then over here, be just the same, but coming out of the page. And you could pick any 2 points that you really want. I just use that as an example. Our magnetic field, by the way, would look something like this. That would be one line. And then maybe this is a second line here. And I'm trying to make the drawing nice. iPad's giving me a little bit of trouble, but hopefully you can see the magnetic field at, say, this end here is equal and opposite to this end here. So I suppose what I'm really trying to say is, in this case, there will be no magnetic force on the loop. And that's because it's going to, anywhere you pick, I'm trying to fix these a little bit. Any point you pick will have a magnetic field, let's say, going in, there'll be an equal and opposite coming out. And you can pick anywhere, assuming it's symmetrical. Okay, so going on to 5. 5 simply says, de Broglie hypothesized that the linear momentum and wavelength of a free massive particle are related by which of the following constants? So this is another kind of just thing you know with the equation. De Broglie wavelength tells us that the momentum is equal to h over lambda. So the wavelength and the linear momentum is related by h. Okay, so that's another definition thing. That's all that is. For 6, an atom has filled n equals 1 and n equals 2 levels. How many electrons does each one have? So the number of electrons is equal to 2 times n squared. So for n equals 1, you have 2 times 1 squared, which is 2. For n equals 2, it's 2 times 2 squared, which is 4 times 2 is 8. So if they have both of these, then it has 10 electrons, 8 in the second level and 2 in the first. So the answer is E, 10. Okay, and then for number 7, this is another kind of equation. Those are kind of nice. You just have to remember which ones they are. The root mean square speed of a molecule of mass m in an ideal gas is given by C. The square root of 3 kT over m. Really just an equation you kind of have to memorize. Unfortunately, there's not really a whole lot to do with that. That's just all that there is. Moving on to number 8, the energy from electromagnetic waves in equilibrium in a cavity is used to melt ice. If the Kelvin temperature of the cavity is increased by a factor of 2, the mass of that ice can be melted in a fixed amount of time. Okay, so for this, what we're going to use is the equation, we'll use J, but I've seen it as other things, equal to sigma t to the 4th. Okay? So this is kind of like the one question we had, like number 3. If we increase it by a factor of 2, well, now it's going to be sigma 2t to the 4th, which is 16 sigma t to the 4th. So this increases by a factor of 16. Okay, so again, this is just another little equation thing you need to know. So for 9 says the figure above represents the orbit of a planet around a star S, and the marks divide the orbit into 14 equal time intervals. So little t is equal to t over 14, where big T is the orbital period. The only force acting is the Newtonian gravitation. Then the true statements include which of the following? Area A equals area B. The star S is at one focus of the elliptical shaped orb. So number 9 is this figure here, which shows the orbit of a planet. This is basically a Kepler question. This is Kepler's 3 laws. The first one being the orbitals are elliptical. That's this. That they sweep out equal areas in equal time. That's this. This area B is equal to the area A. And 3 relates the period with the semi-major axis. T squared is proportional to A cubed. And you can get rid of that proportionality when you include the constant there. So answer choice E. Okay, so that's 9. And then 10 is right here. So 10 says a massless spring with force constant K launches a ball of mass m. In order for the ball to reach a speed v by displacement s, should the spring be compressed. So we can just set our potential energy equal to our kinetic energy. Our kinetic energy or potential energy is 1/2 ks squared. That's the potential energy of the spring, equal to 1/2 mv squared. Obviously the 2's go. And we can say s squared equals m over k v squared. S equals v, the square root of m over k. Which is answer choice B. So that's the first 10 questions. I can definitely do more in the future. if you guys would like. So hopefully that helped. If it did, please subscribe and like the video.